This tutorial will provide an overview of some of the properties associated with the cable object. The cable object is a catenary element with two primary characteristics. 1. All external loads must be resolved into axial forces. The element has axial stiffness only and no bending stiffness. And 2. It is highly nonlinear. Forces in the element are dependent upon its shape. To illustrate these two traits, we have created two cable objects. Each cable spans a distance of 288 inches. The top cable has a sag of 2 inches and a total undeformed length of 288.02 inches, while the bottom cable has a sag of 12 inches and an undeformed length of 289.33 inches. Although there is a relatively small difference in the undeformed lengths, there is a significant difference in the axial forces in the cables. When subjected to self-weight, the cable in the top has an axial force of 1.47 kips, while the bottom cable has only 0.25 kips. In this case, the closer the cable is to horizontal, the larger the axial force must be to support the vertical weight. As just stated, cable shape has an enormous impact on cable forces, so it is important to accurately determine the drape. SAP 2000 offers a powerful tool for the determination of cable shape. Selecting the cable, and then going to the Edit Lines, Edit Cable Geometry command brings up the cable geometry form. The cable geometry is generated from the cable type. The first choice is a shape that gives minimum tension. For a 1-inch diameter cable spanning 288 inches, this tension is 0.06 kips at the ends. The sag for this cable is 97.2 inches in the deformed state. This includes strain deformation, and virtually an identical sag in the undeformed state with no load. The program also tells us the relative lengths for the two states in comparison to the chord length of 288 inches. The program uses this information to generate point coordinates for 17 points along the cable to define the shape. This geometry defines a single element. Multiple elements are not being generated. As a general rule, a single cable element is adequate to model each cable unless you wish to add concentrated loads or discretize mass along the cable for dynamics. The number of cable segments may be changed here. The next option allows for a shape based on a minimum tension at the other end. We can also specify the tension at the eye end. We will input 0.1 kips. This changes the sag to 32.99 inches. Again, we can do the same thing at the other end if desired. The next option allows us to generate the shape by specifying the amount of horizontal tension. Here we input 0.5 kips. This amount is the horizontal component and results in a sag of 62.14 inches. The maximum vertical sag option allows us to specify the vertical sag for the shape. With an inputted sag of 12 inches, the tension goes up to 0.25 kips. The next option allows for the specification of sag to be done from the lowest endpoint. We will input a sag of 12 inches below the lowest end. Now the tension at the two ends is different due to the fact that the ends are not at the same elevations. This is the 12-inch sag that we specified. The next shape generation option is to create a shape based on the undeformed length. If we specify an undeformed length of 288 inches, the sag in the deformed state drops to 1.47 inches and the tension force goes up to 2 kips. The last option available to specify cable shape is to input the relative undeformed length. A ratio of 1 indicates that the undeformed cable has the same length as the cord. Here we will increase the relative length very slightly to 1.001, but notice how significantly the tension force drops and the sag increases. This shows how critical determining the correct shape is to the accuracy of the overall model. And just to reiterate, the only purpose of this form is to find the starting shape of the cable as shown in the coordinates table. It does not determine what forces will be in the cable. Now we will create a model using cable objects. It will be a guide tower 200 feet tall. The single mast tower is comprised of an 18-inch diameter pipe pinned at the base and guide with 3 cables at the midspan and at the top. The guys will have an area of 0.34 inches square with an initial target tension of 8.5 kips. The tower will be subjected to dead load and a wind load of 120 pounds per linear foot. The analysis will be nonlinear, as models utilizing cables always require a nonlinear analysis, and thus the advanced version. We start by defining a grid that is 100 feet wide by 200 feet tall. Switching to inch units, we will define the tower mast. Using the Define Frame Sections command, we will add a new pipe property called mast. The outside diameter will be set to 18 inches with a wall thickness of 1/2 inch. Next, we will define the cable sections. We will call it cable. With an area of 0.34 inches square. Next, we draw the mast from bottom to top. The pin support will be added to the base. We will now add one set of cables in the XZ plane. We draw them so that the eye end is at the ground. This opens the cable geometry form, where we will select a cable type of tension at eye end, as we will use our target tension of 8.5 kips to determine the shape. Repeat this step for the upper cable. Note that the deformed sag is approximately 10 inches, while the relative length for the undeformed case is less than 1. Next, we apply the pinned restraint to the base of the cables. We will replicate the cables and support just drawn at 2 other locations in the model. We will do a radial replication about the Z-axis, placing the cables 120 degrees apart. Now we define our load cases. We will have a dead load case with self-weight, a target case for the application of the target force in the cables, and a wind load case. We will not use the automated lateral load option, as we will apply the wind load directly. Next, we select all the cable objects and go to the Assign Cable Loads command. Here we select the target force option, although we could have also used strain or deformation to tension the cables. We will use a target force of 8.5 kips applied at the ground location to be applied in the target case. Next, we apply the wind load to the mast using the Frame Loads command. The load goes in the wind case, and we will use pound-feet units. The load will be applied in the Y direction with a magnitude of minus 120 pounds per linear foot. The last thing we need to do prior to running the analysis is to define our analysis cases. The program has automatically created 3 cases based on our defined load cases: target, wind, and dead. However, we will need to modify these to obtain the correct model behavior. For the target case, static analysis is okay, but it must be nonlinear since cables are included. The formulation of the cable object includes nonlinear geometric effects, which means that we do not need to perform a large displacement analysis to get the correct behavior for the cables. However, you may wish to consider p-delta for the other objects in your model, such as the mast in this case. In addition to our target cable tensions, we also want to include the dead loads in the analysis. A check of the nonlinear parameters shows that we can set the target force iterations, as well as the convergent tolerance and the acceleration factor, but we will leave all of them set at their default values for this analysis. Next, we will modify the wind analysis case. Again, we will set it to be a nonlinear analysis type. However, in this case, rather than starting from 0 initial conditions, we will start from the end of the target nonlinear case. This will cause the cables and model to be in the correct state when the wind load is applied. We can delete the dead analysis case as these loads are included in the target case. We are now ready to run the analysis. Note that our two nonlinear static analysis cases are set to run. After the analysis, the display shape for the target analysis case is displayed. We will ask to see the axial forces for this case. A right click on a cable brings up the force diagrams, and we see that the force in the cable is 8.478 kips versus a target of 8.5, which is very good. Right-clicking on all 5 other cables shows similar good results. Next, we will display the axial forces due to the wind analysis case. For the first cable, which is perpendicular to the wind load, the axial force is 8.7 kips, not too different from the target. However, for the cable that is only 30 degrees off from the direction of the load, the tension shoots up to 14.6 kips, while the cable that is on the leeward side slacks off to only 2.7 kips. Next, we will show the deformed shape for the wind analysis case. We will increase the scaling to make it easier to see the cable shapes. If we rotate the 3D view, we can see how the cables on the leeward side sag more, while those on the windward side remain taut. Animating the structure gives us an even better idea of the cable behavior. In summary, SAP 2000 provides an elegant tool for the modeling of cable structures, offering a powerful shape finder with many options for generating geometric coordinates, as well as an element that inherently incorporates geometric nonlinear effects. This concludes this tutorial.